So how do you get a piece of hardware to adapt on the fly, or to actually remember what happened just a nanosecond ago? That's the real jump from simple, dumb logic to building truly intelligent systems. Today, we're going to break down how you can build digital circuits that aren't just smart, but also flexible and stateful. And we'll see exactly how Verilog makes all of that happen.
All right, here's our game plan. First, we'll talk about why flexibility is so non-negotiable in modern hardware design and how parameters are the perfect solution. Then we're going to dive into the whole concept of memory and circuits using what's called the sequential always block. And finally, we'll clear up one of the trickiest parts for newcomers, the difference between blocking and non-blocking assignments.
So, let's kick things off with our first big challenge, flexibility. Think about it. In hardware design, you're constantly reusing components. You might need a 16-bit version of a module in one spot and a 64-bit version somewhere else. Having to start from scratch and rewrite code every single time? No way. That's just not going to fly.
This really boils down to two fundamental questions, doesn't it? First, how do we build modules that are easy to reuse and configure? And second, how do we design circuits that don't just process information passing through them, but can actually store it and remember their own past? Let's go ahead and tackle that first question right now.
The answer to that flexibility problem is a really powerful and pretty elegant Verilog feature called parameters. Honestly, these are the absolute key to creating generic, reusable code that you can adapt for all kinds of different needs without ever having to touch the core logic.
Okay, so take a look at this example of a rigid design. We've got a register that's hard-coded to be 4 bits wide. You can see it right there in the code, 3.0. Now, what if we suddenly need an 8-bit or a 16-bit register? Well, we have to go hunt down this line of code and manually edit it. And that's not just clunky, it's a perfect recipe for introducing bugs, especially if that module is used in like dozens of places.
Now check this out. See how we can make this design so much more flexible? Just by adding that one parameter declaration at the top, we've totally transformed the register. We replace that hard-coded number with a variable, n. So now if we want to change the width to 8, 16, or even 128 bits, we only have to change the value of n in one single place. It's beautiful. This is what we call a generic specification.
So what's the payoff? By using parameters, our code becomes way more reusable, readable, and maintainable. All the important stuff you might want to change is defined right up top, making the whole design super easy to understand and modify. This isn't just a neat trick, it's really a fundamental principle of good hardware design. It lets us create these robust modules that can be used in a huge range of applications.
Okay, so we've tackled flexibility. Let's move on to our second big challenge. Memory. How do we get our circuits to actually store information, to have a sense of history? Well, this requires a pretty major shift in our thinking. We have to move from what's known as combinational logic to sequential logic.
Let's break down that difference. Combinational logic is completely stateless. Its output depends only on whatever its inputs are right now. Think of an AND gate. It has zero memory of what its inputs were a split second ago. But sequential logic, that's a whole other ballgame. It's stateful. Its output depends not just on the current inputs, but also on its previous state. A counter is the perfect example here. It absolutely has to remember its current value to figure out what the next one should be.
To build these stateful sequential circuits in Verilog, we use a special tool called the sequential always block. This is the fundamental pattern, the recipe for building any circuit that needs to have memory, from a simple 1-bit flip-flop all the way to a complex state machine in a microprocessor.
Let's just dissect this thing. It all starts with the always keyword. Now, the real secret to its stateful behavior is in the sensitivity list. That @posed edge clock tells the hardware to run the code only on the rising edge of the clock signal. This is how we keep all the state changes in sync. Next up, you've got a reset condition, which is absolutely critical for getting the circuit into a known, predictable starting state. And finally, you have the state change itself. Oh, and did you notice that special /equals operator? Its job is super important.
And that brings us to something that trips up almost everyone when they're new to Verilog. The difference between the single equals sign, equals, which is a blocking assignment, and the less than equals sign, less than equals, the non-blocking assignment. I know they look similar, but they describe fundamentally different hardware behaviors.
Okay, think of it like this. The blocking assignment, the single equal sign, is like a recipe. You do step 1, and it literally blocks step 2 until it's finished. This step-by-step execution is perfect for describing combinational logic. But the non-blocking assignment, the less than equal sign, that's totally different. It's like a flash photograph. At the clock edge, it evaluates everything on the right-hand side, and then it schedules all the left-hand sides to update at the same time. This parallel update is a perfect model for how real flip-flops in a register behave, where every single bit updates at the exact same instant. So the rule is simple. Always use non-blocking for sequential logic.
You really can't overstate how important it is to use the right assignment operator. I mean, don't just take my word for it. As this quote highlights, using the wrong one, using blocking assignments in sequential circuits, can lead to some really bizarre, unpredictable behavior that can change just based on the order of your code. For reliable, predictable hardware, non-blocking assignments are an absolute must.
So, let's wrap this up. We've just armed you with two of the most essential tools in the entire Verilog toolkit. You've got parameters for making your designs flexible and reusable, and you've got the always at post-edge clock pattern, powered by non-blocking assignments for building circuits that have state and memory. By mastering just these two concepts, you have the foundational building blocks to design a massive range of digital systems, from simple state machines all the way up to sophisticated processors. The principles of flexible and stateful design are right at your fingertips. The possibilities are pretty much endless. So the only real question is, what are you going to build?